All right. So like I said, we're going to talk about the fundamental theorem of calculus, which is all 5.3 material. Fundamental because it relates the tools that we've been building up with some really powerful results that'll help us in computation. So it is really fundamental, and also fundamental in the sense that it's fundamental to our understanding of what calculus actually is and what these tools that we've built up actually do. So let's take a look. So it goes something like this, same setup as we've had previously in the course. We have some continuous function f. It's living on a closed interval, ab. And we have the additional information that little f of t is the derivative of big F of t for some other function big F, okay? So this is given to us. We might be able to do this via calculus, right? If we say, I have 3 cosine x, and we remember that the derivative of this is minus 3 sine x, then I can apply fundamental theorem to this little f, for example, right? Because I already know what a function that gives this function as its derivative is. Okay, so what does this theorem actually say? It says for some other function f, if this occurs, then our integral that we've built up is really nothing but just the difference of this other function evaluated at the endpoints a and b. So that should be kind of surprising if you haven't seen that before. And I remember being very surprised by this. I think the reason being is you have some relationship between these functions. One is like, in some sense, the instantaneous rate of change of the other. And then you're asked to find, how much this little function gathers as its area under the curve counted with sine. And it turns out that all that technology can really just be reduced to looking at the difference of 2 values, which is a little bit surprising. So this is a pretty powerful tool, and we'll do our best to work with it. We have some examples. So I like this example because this would be quite hard to compute with other tools, right? We can do it with approximations, it's definitely true, but this would be pretty tedious, right? And we want to do this the best way we can. And if we are able, we want to get an exact answer. And in this case, we definitely can. So here's our integral that we're looking to solve. And the fundamental theorem of calculus tells us that we're looking for some function big F for which big F prime of t, so the derivative of this other function, is the function in the integrand. So is this 2 to the t? Okay, so this is our goal. And if we can do this, we can just apply the fundamental theorem, and then we can reduce this scary integral to something that's very tractable. All right. So our guess is, I won't show you the full slide yet. Our guess is that we know that the derivative of 2 to the t, so looking in the other direction, if we differentiate this guy, we get the natural log of 2 times 2 to the t, right? So this is a familiar differentiation rule for us. So our guess for this capital F of t should be something that maybe looks like this, but without the log of 2, right? So if I divided my initial function by log of 2 preemptively, because I know that when I differentiate, I get a log of 2, then these things are going to cancel. And that's what's happening here. So I said, well, I get a log of 2 when I differentiate, so why don't I preemptively divide by log of 2? And then here, because I've preemptively divided, log of 2 times log of 2 is, of course, 1. So we get what we want. We get 2 to the t. Okay? So this is very good because now we can apply the fundamental theorem. So the fundamental theorem tells us that once we have this capital F function, all we have to do is just plug in the endpoints and subtract the difference. So here, 2 to the t at the endpoint 1 becomes 2 to the 1, again over ln 2, and 2 to the t becomes 2 to the 0 at the endpoint 0. So this is at 1, this is at 0. And now we just have the difference of two fractions, right? So this is, of course, 1 over the natural log of 2. So that's kind of amazing, because before we were doing all this like rectangle stuff, and sometimes if we can't get an exact answer, that's the best we can do. But here we can get an exact answer for the area under this curve, just using what we know about calculus and nothing else, which is kind of amazing. So really, that's it for this lecture. So I'll stop there before I maybe do just a couple more examples. But let's see if